Hi there, this is Group15's presentation on BigMAC, Fine-Grained Policy Analysis of Android Firmware with Thusi, Malathi, Nirosh Kumar, and Tom. To defend against malicious applications and external attack, Android relies upon a complex combination of access control mechanisms to maintain least privilege. To understand the impact and interaction between these layers, the authors created a framework called BigMAC, which combines and instantiates all layers of the standard Android security policy into a fine-grained graph supporting millions of edges. The model the authors developed filters out paths and types not in use on actual systems that policy analysis alone would consider. The Android access control framework includes a discretionary access control mechanism and a mandatory access control mechanism through Security Enhanced Android, a customized version of SC Linux. To maintain the integrity of the Android operating system against local and remote adversaries, however, these mechanisms must work together, and this is why the authors developed BigMAC. BigMAC recovers system init scripts and simulates the behavior of commands that affect the file system in order to accurately model file system context and Android credentials. The authors demonstrate that, compared to the data retrieved from a running Android device, BigMAC successfully labels and reconstructs over 98% of DAC and MAC file system metadata and up to 74.7% of running process metadata. BigMAC was also able to determine potential vectors of attack based on policy inconsistencies found, and the authors were able to demonstrate that several exploits can be modeled with it. Let's recall the Linux access control model. On Linux systems, DAC has been implemented using object ownership and group membership, and the respective read, write, and execute permissions. Privilege separation is primarily based on user ID and group ID assignments to processes and file objects. Permissions are assigned to new and owned objects at the discretion of the users. This means that the system's access matrix is not fixed at runtime and may change dynamically, possibly leading to a loss of integrity. To help limit the damage that a root process may incur, the Linux kernel divided up root permissions using a capability-based system. This capability model works with some applications, but its lack of granularity can still lead to over-permissioned processes, which can be dangerous when working alongside untrusted processes and users. To further lock down Linux-based systems, a MAC scheme can also be deployed, the most popular implementation being Security Enhanced Linux, or SC Linux. Unlike DAC, MAC has strict control of actions taken by objects and is fixed at runtime and enables the security policy to be written and verified statically before being applied to a running system. SC Linux has three core components. Subjects are an active process or device which are given access to objects via allow rules that permit the subject to read or modify the object, leading to changes in the system state. Objects are resources such as files, sockets, and network interfaces which are accessed by subjects and classified according to the resources they provide. To determine whether a requested action is allowed by the policy, the operating system can query both subjects and objects and their set of security attributes. The Android security model. Android's kernel uses a modified version of Linux that implements DAC and involves a fixed set of user IDs and group IDs for system processes, and a fixed range of user IDs for dynamically installed applications. Android limits the number of processes running as root. High privileged processes are usually running as a system user or a role-specific user ID. It denies most running processes access to root permissions unless they have been explicitly granted or inherited these capabilities. Let's talk about SC Android. SC Linux was introduced to the Android platform with a targeted policy in 2013. SC Android extends SC Linux to support new Android-specific hooks. The core functionality is mostly unchanged, with the primary goal being mandatory system-wide type enforcement. The SC Android user space introduced modifications to existing SC Linux components which enforce the security policy being beyond the kernel layer and include the init process, which is responsible for loading the security policy, the zygote, which is responsible for spawning Android application processes, Bionic, the Android C library, which is able to get and set extended file system attributes and store file security labels, and the package manager, which determines if permissions requested by an application can be actually granted. All of this will be discussed in more detail later in our presentation. Let's talk about Android middleware. Mobile application developers have moved away from implementing system access control models and instead focus on Android middleware permissions. These are capability-like and grant applications access to resources and services provided by the Android operating system, not the Linux kernel. The authors of this paper did not examine Android middleware permissions. They instead focus on the combination of DAC, MAC, and capability-like permissions and their impact on the security of the system as a whole. And now I'll pass the presentation to Thusi.
Thank you, Tom. Hey class, this is Tushi. I'm going to explain about the design of BigMAC. So to begin with, why BigMAC was designed? So it was designed so that we can able to estimate query the security policy of an Android firmware, right? So author designed the BigMAC in a way that it can extract, recover, and simulate a fully instantaneous of all the objects, which include file, process, users, and all kind of stuff that we need to attack a system from an Android firmware image. So the BigMac, it's operate right off the Android firmware directly, right? And it's extract. So how it's do it is extract the file system first, and then the files within them. From here, it's extract the label on the files, which include the DAC, cap, and labels, and also which allow to rebuild the graph and interaction between the different process and object in the system, right? So this help the SC Linux policy, which is type of graph, which will help, this will help us to understand the relationship between the different component inside the system, right? To get like the more fine graph of it, to get to know more process and files and IPCs, right? So from here, author explained that they fully instantaneous the policy graph and inject into the BigMac core engine. So this will allow us to get the attacker's graph, right? So to understand the more relationship and how the attackers can able to take the privilege of the component, right? So that's what the author begins with. So let me talk more about in the file system and how that author get into it, right? So pricing all the extracted information from Android firmware into a multi-directional graph representations, like a combination of all types and attributes used in the enforcements of the SC Linux policy. So the author divided into two, so subject and object. So for example, object is like a file, directory, and path, and the object is like domain, which users belong to the accessibility. And in here, the attacker graph. So I'm going to explain about the attacker graph, right? So building an attacker graph is composed of many steps, starting from SC policies and backing up files, which we have extracted from injecting the BigMac, and also it will create the subject graph, right? So the subject graph is like a coarse grain graph, is linking all the possible subject in the system. Then quickly it translates into the data flow, which the graph is having a fine grain of understanding of the subject. It's pulled down like a read and write relationship, which matches the privilege escalation model, right? And parallel to the data flow, there is the process tree. So this is like creating a process tree so that all the process associated within every subject and object, and parallel to the process tree there's a flat data flow, and which is overlay the full instantaneous of attack graph, right? So the next is the query construction space. So author designed the Prolog based query engine as a backend, so providing a multiple query interface to the end user. In the below, it shows the four queries like a query max, query mac dax, query mac dac caps, query mac dac caps X, right? So for example, in here we shows that the query mac dac caps extensions passing in these arguments like a cycode process, three cap system admins, and USB and P, right? So in this example, it clearly shows that this particular query is targeting the cycode process and pass both MAC and DAC checking, having a maximum path length of 3 and achieving with the cap system admin capability, and can able to launch it from USB connection. That's why it says we pass the USB here, right? So query construction, so as I mentioned in the previous example, it's passing all those, but at the back end, I said it passes through the four query, right? So if you see it here, those four queries are right underneath right here. So finding a path, and then it's passing an argument and graph travel, DAC path, cap path, and ext path, right? So DAC path P is passing, and so what DAC path do is predict and check the corresponding DAC policy by looking into every adjustment of the pair of nodes within the DAC predicts, right? And then cap path is passing two arguments, which is the it's predict and check if the given path can acquire a certain Linux capability of particular jobs. And XPath is like predict and check if the given path start from an external attack surface, for example USB or Bluetooth or whatever it is, right? So pretty much that's all the design of BigMac. And now I am passing down to Niroj. He can able to explain you about the implementation. Thank you.
Thanks, Tushi. And hello everyone. Let's look into the BigMAC firmware implementation. So the BigMAC firmware is constructed based on Python 3.5 and SWA Prolog APIs. So it employs the Network X library for the graph construction and the SE tool package for decoupling the SE policies from the Android images. So the implementation comprises the four blocks: the firmware extraction, the system boot emulations, and Android credential simulations, and logic-based query engine. So here, author uses the open source extraction library for the raw form. It supports 18 firmware vendor, and they extended to support Samsung image as well. So, but the author primarily focusing on extracting the Google, Samsung, and LG images. Yep. So, as part of the extraction tool, first the recursively unzipping each layer of the images based on the file type, and using the ext4 disk image extraction routine to maintain DAC and MAC information as well. So in the second, this tool does a walkthrough on each image and fetches all the metadata provided by the three API calls called state, getX, attributes, and readline. So these all extracted metadata will be stored in the dictionary file for the further process. And then using the virtual system, the author will extract every file including build.pop file. So all the files in this image, as well as the build.pop, which encompasses metadata such as Android versions and hardware configurations. So finally, all these extracted raw files will be stored in their image specific database for further processing. So after static firmware file extraction, the author emulates the Android system boot. But the issue is the author doesn't know the process running on the firmware. Yeah, so the author says that to understand how the system policy would apply to these processes, we should know what are all the processes running on the real phone during boot, including their permissions and the runtime credentials. Without knowing this, the cross-vendor analysis would fail on the scaling. So here the Android booting process is well defined by the platform. That's it. Yeah. So Android kernel starts similar way as the desktop Linux kernel starts. So in its very first process, we can say it is a root process or grandmother of all the processes. So init process has two responsibilities. One is to mount the directories and then running the init.rc scripts. So author mimicked the init.rc and they implemented the commands such as mkdir, ch1 and chmod. Change the state of the file system including the DS information, and followed by trigger, it rises an event, and the enable command, it starts all the booting services, and followed by the mount command, it's mount all the file system to the hard point. Yeah, so there is a little challenge in booting emulations. So here the each vendor and device model comes with its own set of behaviors in the init system. So for instance, the Pixel 8.1.0 image during the system boot, it creates a slash data directories. For author to do this, for author had to set the property called the whole decrypt to trigger the post decryption in the init actions. And the second one, the author discovers another behavior associated with OEM, called the original equipment manufacturer. They add their custom groups and user IDs that deviates from the Android platform, so which is unable to map these names to the existing IDs in the extraction Android files. So to fix that, they are extracting the Android IDs from the Android libc.so binary file in order to just overcome these all challenges while emulating this boarding system. In the credential emulation, after booting init and modifying the file system, the author recovered the service definitions from the init files to properly assign the runtime credentials to inflated processes. So these service definitions contain, in the Android users group and capabilities information. And followed by here, as part of the logic based query engine, the author used the SWA Prolog 5, constructed this logic based query engine and provide all four query interfaces to pass the output from the Prolog, which means the list of paths. Yeah. Then the author created interact query frontend using the GNU readline library. This gives us support for the interactive tab completion of all the possible processes and objects to use source and target nodes, and also allow us to save, restore, and print all the queries. So within Prolog, the author needed to add cutoff parameters to prevent length values is beyond the values specified, which means the path values. And the author also implemented is unique, which is used to filter the paths that contain duplicate elements. And then to collect all possible paths, the author uses the Prolog's depth first search DFS with interactive deepening. Yeah. In total, the author wrote of 5,997 lines of Python across the extraction tool, graph, and creators, and query frontend. And as part of the Prolong engine, they were written, 343 lines. So that's it. So let's Malvi continue the remaining part of the paper.
Thanks, Nirush. I'm Malti, and I'll walk you through the evaluation and analysis of BigMac. So the idea here is to try and recreate the Android runtime system state from the firmware. So shown in the table, they were able to fully replicate some of the major directories like vendor, system, dev, and so on. Comparison targets were Samsung S7 Edge 7.0.0 and Pixel 7.1.2. So they first recovered all the files from the physical devices that did not have root on and compared them with the corresponding firmware images that they got online. So the authors got 98% of it right just from the static firmware alone. So they had a pretty accurate representation. The second part of the ground truth evaluation was the comparison of recovered processes, and it was noted that they achieved 75% accuracy just from the boot time simulation, and a comparison of the processes recovered by BigMac versus running devices process extraction is shown here. So in the first figure, correct means how many recovered processes had 100% identical metadata, excluding the process IDs, so as compared to a running phone. Different DAC or cap is where a process was matched to a running device process, but part of the DAC capabilities were different. Extra means the processes that BigMac had over approximated. So these processes were not actually running in the system, in the real running system during the snapshot. Now in the figure B, pair found shows how many recovered and real processes were able to be matched through executables and the SA Linux context. The ones labeled missing native are the native daemons that were not instantiated at all. And the missing app are the zygote children that are not currently recovered by BigMac. So they are the zygote applications that were not recovered by BigMac. So the authors develop an interactive query interface having all possible information about the different possible paths meeting these query parameters. So as shown here, the query params are source node, target node, maximum path length or cutoff, target capabilities, and object type. So to strengthen their analysis, they generate attack graphs from two different images, one of Samsung S8 or higher version, or the other one with LG G7 firmware. So to demonstrate the path reduction, including DAC checks, the authors ran a query with both MAC and DAC filtering using an untrusted app along with the WAL-D process. So as shown in the table, they were able to bring down the number of query results by providing multi-layer filtering. And they chose the WAL-D process because it is a powerful Android platform daemon responsible for mounting and managing disk volumes, and it's considered to be a vital part of the Android's formal TCB definition. Now, Zygote is a process, a special process in Android which handles the forking of each new application process. So the authors analyze CVE 2018-9488. So the flaw was it let the Zygote process compromise the crash dump. So crash dump can easily read and write the memory of WAL-D using the ptrace syscall. And so this was allowed by the MAC policy. Now coming to the process strength, this table shows the top 3 processes in each device. So if you see here, the authors used S8 and LG G7 for their comparison. So it basically demonstrates what the process can write to. So it would be ideally writing to files or IPCs and so on. So the main inference from this analysis was the system server process, which pretty much interacts with a lot of applications and is quite powerful. So any bug in this would be compromised easily, and it can attack further parts of the system because of its implicit trust. So the author's recommendation was to refactor the system server to smaller processes which have much lesser privilege, something similar to the media server process. So as a conclusion, the authors developed BigMAC as one of the most fine-grained policy analysis frameworks using just the static firmware. And using layered path reduction, BigMAC surpasses the older Mac-only policy analysis frameworks. And finally, it also examines the strengths of processes and has the ability to investigate the privilege escalation paths as well. So that was it from our end. Thank you.
These are the references. Thank you, everyone.